Good evening, and thanks for joining tonight's TI Technology webinar, where we're getting ready to go back to school using the TI Innovator Hub. My name is Mike Houston, and I'm the moderator for this event. I teach algebra and calculus near Pittsburgh, where I use TI technology to make tough-to-teach, tough-to-learn concepts accessible to all my students. I'm really excited to introduce our two panelists for tonight, Stacy Thibodeau and Todd Graba. Stacy holds a bachelor's in science and chemistry and a master's degree in educational leadership from the University of Louisiana at Lafayette. She has been in a science classroom for 17 years and currently teaches at Southside High School in Youngsville, Louisiana, where she teaches all levels of biology. She has also taught biomedical science courses in Project Lead the Way and chemistry, as well as AP. She uses TI technology to assist her teaching, data collection, and modeling math concepts, linking them to science content. Stacy, thanks so much for being with us.
I'm so happy to be here. I actually start school tomorrow with students, so I am eager to get this going to see how other people may want to use this in their classrooms. Thanks, Mike.
And Todd is the STEM division leader at Crystal Lake South High School in Crystal Lake, Illinois. His teaching background is in physics and chemistry, but he has extensive curriculum experiences in all high school math and science practices. Todd's main professional development areas for TI are in using the TI-Nspire as well as the TI Navigator systems and science classes, and with incorporating coding into the classroom or STEM activities with the TI Innovator Hub. Todd, thanks so much for being with us tonight.
Absolutely, Mike. I'm glad to be here, and I'm hoping that everybody can take away a little something here where you can see how you can use coding in the classroom just as a standalone activity, or also to help reinforce some of the content that we're trying to teach in our math and science classes.
We're expecting a large crowd, so your audio is muted. Feel free at any time to send any questions to Todd or Stacy using the Q&A window on the right side of the screen. We'll also be using the chat window to send general messages. As a reminder, you'll receive the certificate of attendance at the conclusion of the webinar. You'll also receive the documents that are being used tonight at the end of the webinar. And this is being recorded, so it's going to be best that you just follow along, really just watch what Stacy and Todd are doing tonight, ask questions if you have them, but following along with your handheld or your software is going to be best to do with the recording. That way you can go at your own pace, and that recording will be sent through email within a few days. We hope you don't have any audio issues, but in the event that you do, try selecting Communicate from the WebEx menu and choose Audio Broadcast. And if that doesn't fix your audio issues, in the participant window where your name is located, there's a small little phone icon in the lower left-hand corner of that window. If you click that phone icon, it'll give you information that you can use to call into the audio portion for the webinar. At this point, Stacy is going to discuss our agenda.
We did welcome and introductions. Just want to make sure everybody is comfortable tonight. We have a lot of information to share with you guys about writing basic code using TI Basic with the Innovator Hub. We're also going to do it two ways. We're going to use the TI-84 Plus CE and the TI-Nspire, so that both platforms will be used tonight. We're also going to look at one of the Pathway to STEM projects that incorporates the software and hardware to help deepen your and your students' understanding of coding, wiring, and graphing. We're going to show you guys some online resources that are free, that are tried and true in classrooms. Both Todd and myself have worked with them. And then Mike's going to give away a registration for two to the 2018 T-Cubed International Conference that'll be in San Antonio, Texas in March.
Thanks, Stacy. And Todd is going to discuss our expected outcomes.
Yeah, hopefully by the time we're done here tonight, we will have introduced the basics of coding to build students' critical thinking skills and deepen their understanding of STEM concepts. I think the critical thinking skills is something that we all look to bring into our courses, and through the coding and some of the thought process that go with it, it only deepens students' understanding and helps them hopefully take these skills into other areas. we will show you how to write a couple of very basic programs using some of the sensors, the built-in LED light and the brightness sensor on the Innovator Hub. And then we'll show you some resources and get into an actual project that is available to you to use with your students on the website. And we'll take you through the coding both with the 84CE and the Nspire CX for how you can write the code, and then show you how what the program actually will produce from there.
Todd, thanks so much. Stacy, it's all yours.
All right. So like Mike said, he is going to send you guys this presentation. It's kind of hard to show coding and the Innovator all live. So like he mentioned, you may want to just kind of watch, maybe take some notes, and then when you have time, go through this on your own. So Todd and I's information is listed there. That way you can get that. One big thing I know for us in Louisiana is moving to some new standards. We're not an NGSS state, but we are adopting new science standards. And I really like this slide, this graphic, because I think sometimes when we are focusing on our classroom and our content, we forget that there are practices in both the other areas as well, ELA, science, and math. And so things that we're going to be doing in science tonight, we're going to ask questions and define problems. This whole engineering design we'll talk about. But math does the same thing. They make sense of problems and they persevere in problem solving. And then with ELA, they're going to demonstrate independence. And that's really what we want our students to do. We're not trying to make programmers out of every student, but this independence, problem solving, perseverance, I think are big areas for us. Modeling with math is big as well for mathematics, but then in science we're going to analyze and interpret some data, and we're going to look at some tonight. And then comprehension and critiquing is big with ELA. So I just wanted to kind of throw that out there, that we don't forget our ELA counterparts that may be down the hall with us, because we can actually look at the three practices together. Like I mentioned about looking at the next-gen science standards, but also looking at Common Core state standards. And I know for some states, especially big in Texas, they have their own standards, but we kind of all speak the same language. Common Core says we're going to do some make sense of problems, and NGSS says we're going to ask questions. We're going to construct arguments in Common Core. In NGSS, we're going to argue with evidence. And hopefully tonight, Todd and I are going to show you that we can actually achieve all of this through TI, not only with coding and the Path to STEM projects and this engineering design, but the other components that are available for you that are free on education.ti.com website to actually help guide you in some of your practices in your classrooms. So engineering design process, I was at the Houston Summit last week, and I actually had some teachers there that work with engineering design in their classroom. They're like, Stacy, I love this slide. I've seen it and I have like 12 steps. Well, this is really just a sweet, concise way to work with students for the design process. I know with us in science, a lot of teachers are like, hey, I'm not an engineer, I can't do this. But we do it all the time. We actually call it scientific method or new way, the science and engineering practices. And so we just want to ask a problem or what is the problem and ask questions about it. What are our constraints? And Todd and I are going to show you guys that with some of these Path to STEM projects. Brainstorm and ideas. We want the students to start thinking, how do you choose the best? Plan, draw a diagram, create and follow out that plan, and obviously improve, and we want to communicate. So again, if you're new to the engineering design process, whether you're in your math or science classroom, maybe this could be something, a graphic you use with your students, or at least just keep it for yourself when you're trying to develop some lessons.
And engineering design is obviously a part of the NGSS standards. It's one of the main threads in there. And I think some of the time when we struggle with what is engineering in our classes, the two big things I take away from this are, number one, what are the constraints? There are always constraints. It could be time, it could be money, it could be budget, it could be materials, but there needs to be some kind of constraint in the process. And then the improving part, I think, is a spot where we tend to stop a lot of times in our science labs, where we perform the lab, we get the data, we write a conclusion about it, but then what? So the improving step is really that next step in the process, or as we'll talk about here with the code, changing the code. How could you make this work differently? What would happen if you tried this? And that's where that gets brought in with the engineering design process as well. The Innovator is the product we're using tonight. I'm not sure how many people have ever played around with it or used it, have any experience with it at all. So just some basic ideas of it here. Down in the bottom right corner, you can see a picture of the hub, and we'll take you through some better pictures also as we go, and you'll see some of the ports in there. But these are all the built-in pieces to the Innovator that come with it, designed inside of it, and it's got a transparent top so you can actually see a lot of the hardware that's inside. But it's got input and output ports that you can put a variety of different sensors, motors, different devices that go with it. There are breadboard connectors built into the hub itself, and then you can also connect it to breadboard. So there's quite a bit that you can do with building and the projects, as you'll see as we get moving here through the presentation. There's an I2C port for, again, throwing in some different sensors, different products that use that connection. The mini USB port is what is used to connect the hub itself to your 84CE, the Nspire CX, or if you are using the TI-Nspire teacher software, you can code through there as well. There is the micro USB power port. If you're using a servo motor with this, for example, the built-in power of the hub itself is not enough, so you need some external power, and that's where you can put the external power into. There's a red LED light, which Stacy will show you a program just to turn it on and off here in just a second, but that by itself is fascinating for a lot of kids. There's a red, green, blue LED where you can turn on any of those or different brightnesses and sensors with that. There's the light brightness sensor, which I will show you some code for here in a program with that in just a second. And there's also a speaker which you can use to produce different sounds and frequencies and make songs with it and all kinds of amazing things that kids love to be able to create. One of the things to consider as you're going through is we want to make sure that your systems are up to date. Now is not the time, if you're following along with us, to do the updates, but this is all here with live links to make sure that your operating systems are all up to date. So if you have the 84CE, you need the operating system shown there, the 522. And with the CE, you need the separate Hub app in order to do the programming. So you just need to go on. It's the same link. We'll get you the Hub app, but you'll need to download and install the Hub app onto the 84CE. With the Nspire CX, with that operating system, the programming is already built in as one of your options for the documents, and you'll see that. But that's the newest operating system for the CX. And then also the Hub goes through a variety of sketches. It's a relatively new product on the market, and so as TI works to improve it, different sketches are brought in, which generally makes it more functional or reduces the amount of coding that you need to do in order to make the Hub itself work. So that's the link to get the new sketch to update for that. So we're going to take you through two different programs. We have a lot of users that use the CE and the Nspire, so we want to make sure that we show you both of those two. So Stacy is going to show the program just to turn the red light on the 84CE, and then I'll come back on and show you how to code the brightness sensor, show you a video in both cases of it working, and then I will take you through one example of just some live coding so you can see the menus in action before we jump into the actual project for tonight, which we will show you here in just a minute.
So first of all, I teach biology. I'm moving to a brand new school. I've taught all levels of science with the exception of physics, which that'll probably be coming in my new school pretty soon. And I got into this because it was exciting to me. I took Fortran programming in college and never used a minute of it. But the coding and the programming and the engineering process is exciting to me, and it's exciting with kids. So initially when I started with this, I was like, okay, I can't do this. I'm not a programmer. I just teach science. And then when the projects started coming in, they started being developed, and I could see a use for this in my classroom. It's that piece that was missing, I think. Yes, there's content. Yes, you have to solve problems. I taught chemistry, right? So you have to balance equations and stuff. Last year, we actually built a conductivity meter with the Nspires and the Innovator and a few little wires and breadboards. And the kids went ecstatic because they were able to manipulate data that they collected from a sensor that they built. So totally different mindset, than from what maybe we've done before with conductivity sensors. So anyone can start just like I did from the basics and learn from there. So this is using the TI-Innovator CX. And so I have a video. I'll kind of walk you through it. I'm not a videographer. I did this while the 3 kids were screaming in the background. So I'm just going to play the video and kind of explain. The program's written for you on the left-hand side. It's a basic program. You're going to send a message to the innovator to set the color red on. I used the RGB LED, and then I waited 1 second so that the color stayed on. And then I send the message to set the color red off, and we see it came on and it came off. A lot of people are like, hey, that's not a big deal. All I did was turn a red color on. But it is, because you were able to do 2 functions. You set it on and you set it off. And so what we're using is the TI basic language. It is all menu driven. And so I don't really have to understand or know code. I understand the flow, and I teach my students the flow of the language and what it means to set a message. But at the same time, using the TI basic, a lot of my students who probably never would have been exposed to computer programming or any kind of computer science have the ability because of just having the handheld. So you'll see Todd will now show you next with the Nspire, and it's a little different, but it's still the same language using the TI basic. So here's Todd's video.
So this is just showing the brightness sensor in action. There's the code for it, and I will actually rewrite this code for you so you can see it. There's about 7 or 8 lines of code, 9 lines of code that you can see in the upper right-hand corner where it says 4 out of 9, and my 2-year-old just came in and tried to get my attention. Running the program here, I then took my iPhone with the flashlight on and I brought it near the brightness sensor. It started collecting the data as the light is getting closer, becoming more intense. The amount of brightness that it's reading is increasing. And then they're written into the code is when the brightness gets to a certain level, it automatically shuts off. And so that's when I came in and covered up the sensor, and once we got below the level that I set, the sensor turned off. In a previous webinar that I did where I incorporated a piece of this video in it, I was then, just from a content perspective, I was able to copy that list of displayed terms into a spreadsheet and then make a data and statistics plot of it. And as the light got closer and the intensity got brighter, it made a perfect inverse squared relationship, which is what we're trying to get to. One of the things you're trying to get to with brightness and how distance and brightness are related to each other. So a lot of content connections that can be made from here. And one of the things that Stacy mentioned, and I'll reinforce as well, is like her, I took one Fortran class, and that was back in, gosh, a long time ago, back in the 90s. Before I got into the coding with this. And so I am not a computer scientist. I am not a programmer. But again, I can reason through, I can look at the code, I can create it. And I think that's one of the areas where sometimes we tend not to bring something like this into the classroom because we feel like we are not the experts in it. You don't need to be the experts in it. We have materials put together for you that you can follow through and kids can do. And it is amazing once you get some of this in their hands where they take it and the ideas they come up with and what they do and how they can create things. And oftentimes it's the students that you do not expect are the ones who come out with just some incredible programs. And I'm constantly learning from my students when I bring this into class to reinforce the content that we're trying to learn. Stacy said she's not a physics teacher. I am. And this is a perfect activity for a physics classroom to try to get that inverse squared relationship across. As she said, it's menu driven. And here are some screenshots of the menus. But I am going to pull up the teacher software and actually go through so you can see where those menus are. So Stacy, if you want to put me in control here, and then I will share my screen.
Yep, you're in charge now.
That's a scary thing for a lot of people. All right. So using the teacher software, it doesn't matter if you are using CAS or non-CAS. It really, it's relevant for this. If you're using Navigator software or not, just use any version of the teacher software will work. When you create a new document, with the latest operating system, Add Program Editor is one of your choices. And so you're going to create a new program if you haven't done it before, and you're going to name your program. You can name it whatever you want. I'll just call it Bright One. Hit OK. and that automatically creates the program for you. If you notice right away, it's define bright 1. What a common mistake I see a lot of people do when they first start is they begin to write their code inside of here. If you have arguments that you need to define in the program or that you're going to call for from the user of the program, you can put them there. But generally, you're not going to put much inside of the parentheses there. Where you write your program is actually between the program and end program. So all of this is set up for you ready to roll. When I save this at the end, the bright 1 is stored as a variable. So I'll show you in the, once we get the program written, where that then, how you actually run the program within the window here. So I'm going to show you the same code that I had on the screen. One of the things is when we start the program, we want to display what the program is doing. So you can do that by putting in a command that says display, and then you put in the string that you want displayed. The string is what is inside of the quotes. So display light sensor. And then this is one of the areas where you can either tell students up front, if they're seeing the code, what the purpose of this line is, or ask them to try to figure out what this code is. Because in the next step, so I took the number 2 and I stored it as B for sensor, is we're going to put in a loop. And that loop is going to be a while loop because we want to get the data while this B value, the brightness, is above a certain number. And once it drops below that number, then we want the program to turn off. So in the menu, we'll go into the control area, and all of these loops, again, are already here for you, ready to go in. As Stacy said, it's all menu-driven. And I'm going to choose a while and end while loop. And so while what that does is it creates the loop strand for me here, and then I just need to put in the parameter while what. So I'm going to say while B, that number that we stored as 2 before, is greater than 0.25. Now the brightness sensor in the hub doesn't use lux for this. It's its own system, its own setting that's built in. So the activity we're going to show you in a few minutes here is a calibration activity where we're actually going to read voltage and convert that into temperature through calibrating. You can do the same thing here where you can use the brightness that's displayed and figure out how to convert that into whatever brightness unit you want to use. So we're going to set the parameters again as while the brightness is greater than 0.25. So we put the initial conditions of the brightness as 2, so that way the while loop will initiate. So questions you can ask kids here are what is the purpose of this 2 stored to B? You can ask them what would happen if B was 0.2 instead of 2. A variety of different areas you can use with it. You can ask them, do we need to have B as 0.25 based on the amount of ambient lighting that you have in the room? Maybe that's too high or low. So areas, again, that you can adjust, fixing that problem, asking those questions, looking for solutions, all part of the engineering process. When I come down here, I like to indent inside of loops. It just makes it easier to read the program. You don't have to. You can do it as a straight line down, but it helps me visualize what is actually inside of that loop. So what we want to do is we want to send a command to the hub. Oop, hang on a second. Not to do that. Sorry. We want to send a command to read brightness. And anytime you do a read command, it's not only does it going to read it, but we have to do something with that. So you have to tell, anytime you do a read command, you have to put in a command that is going to then get that value. So we initiated the B value. We said while it's at a certain level to go ahead and do this loop, we're going to read the brightness, and we're going to get that brightness then from the hub. Next, I want to know what that information is. So I'm going to ask for that value to be displayed. So set the parameters, read the brightness, get the brightness. Now display that on the screen. And then I want this to happen every certain amount of time. I want there to be a little bit of a delay. Again, you can play with the delay and figure out how long that's going to be between every time that the loop goes through. So I am going to put in a command that says wait a certain amount of time before doing this again. And the command that I had in there was for 0.5 seconds. That's the whole program, a very simple program to write. Based on what you want the kids to do, if it's a coding assignment, you could tell them, here, write this code. If it's to learn what code says, you can provide them with the code and ask them to modify it. So whatever your goals are, you can do within the code itself, because you'll save this as a document that you can send to students or have them created. Again, it's up to you and how you want to run your classroom. Control B will store the syntax and store the program. And then to run the program, you need to start a calculator page and then call for that variable, which we called Bright1. And if I were hooked up to the Innovator now, I would just hit enter. It would run the program. The values would run until it got below 0.25. So a simple program to show you how you can build some code in there and see those menus that Stacy and I have referenced. I am going to stop sharing this and send it back over to Stacy since she has the PowerPoint, and we can get back in the presentation.
Thanks, Todd.
Stacy, before you jump in, I just want to remind everyone there's a lot of press this, do that, which just again is as a reminder, you're automatically going to get a link to the recording in a few days. So that's really the best way to follow along with this, and that way you can go at your own pace and go step by step.
Thank you, Mike. So another thing that we wanted to make sure that you were able and to have access to and to see are the activities that are already on the website. So they are hyperlinked. So we first start out, what I did with students, and I'm sure Todd did the same, was what's called 10 minutes of code. And maybe 2-3 years ago, coding became really big in all high school classes, and they said, hey, can you give us 10 minutes a week just to do some coding? And so TI has some that are just specifically for the math aspect using the 84 CEs or the Nspire. Then when the Innovator came out, they also have the 10 minutes of code for the Innovator. Also, both for the CEs and the Nspire. So those are available for you. They are completely free. There's little short videos that you can watch with the student, or if you want to ahead of time. There's teacher notes that have a lot of the code already written for you and kind of walk you through some teacher tips. So kind of, if you're a little nervous about doing it, you can try it yourself. And then also with the science and engineering design process, there are the Path to STEM projects. And so Path to STEM projects, that's what we're going to do tonight. The Path to STEM projects, again, are both for the 84 or the Nspire, 84 CE, excuse me, has some videos, has downloadable files. And the way these work is they are units that build skills, 1 to 2 to 3 skill builders, and then there's a project at the end. And so you're applying your knowledge, or the students are applying their knowledge of the skills, and then can apply them to a project at the end. Starting with basic fundamental sending and getting, just like we're going to do tonight, all the way, and the one we're going to do tonight is this calibration. So not only we're going to send and get, but we're going to calibrate a digital thermometer using an analog sensor. And so these are completely free. They are on the website, and then we've also provided links for you as well. And so what I did with my students was in my classroom, I only did a few of the activities because I was so content driven. I wanted to make sure, I covered my content, but I had a STEM club, and then I did a STEM camp this summer, and I really let them just play, having them learn a few skills, and then it was, hey, Ms. Tibb, what if? And I said, I don't know, just do it. And then what's the code for this? I don't know, let's try it. And so just like the presentation says, you can edit it how you see fit, and these are just launching points. These are just there to give you some background information, because the majority of us out there are not computer science teachers, and you can add on to that based on your comfort and your abilities. All right, so the project we're going to do is Project 5, like I mentioned, and so we kind of organized it, right brain, left brain, not really, but left side of the screen is going to be for the 84 CE, right side is going to be for the Nspire CX. And so this is written for you so that you can understand at the top, kind of, I tell the kids, like you would read it in an instruction book, and then at the bottom is what the screen would look like if you were doing coding. Again, all menu driven. And so we are going to use the breadboard connector part that was mentioned earlier, the 20 pins. There are 10 pins along with some grounds, and then you can apply some extra batteries if you need. And so we want to connect the hub to the breadboard. And so everything on the 84 CE is under the Program tab. And so we would name a program, and then we're going to send connect, just like we talked about earlier, where we send set. Well, this one we need to connect to it. And then we're going to connect analog, because it's an analog signal, and we're going to connect it to BB5, which is breadboard 5 pin. The biggest difference that is hard if you're both an 84 CE user and an Nspire user is that for the commands with the 84 CE, it is best practice to close quotes, close parentheses, because sometimes if you don't close both, it doesn't work very easily, and I found that the hard way. Todd?
So on the Nspire CX, you'll notice that the commands are pretty similar. Both Stacy and I, and most of the people who have used this, we go back and forth between the two different platforms. I was originally trained on the Nspire CX. Then I ran a training session on the 84C, and it was very easy to go back and forth between the two of them. So whichever platform you're most familiar with is fine. Or if you're like in my classroom, I typically have multiple different operating systems going on at the same time. And so I'll have some kids that have the CE and some kids that have the Nspire, and I kind of have to be able to go with both of them. And a lot of the programs that are written online can follow both of these two, and kids can pull it specifically for the operating system they want, or it may have both of them written out just like we have here, where the 84CE is on one side and the Nspire is on the other side. So for this, you'll notice that the commands look very similar to each other, except here we define the name of it like we did before, and it has the program and program window like you saw when I did the live coding. And then we have to, again, send the command. Analog command 1 is the name of the command. Notice that's not in the 84CE version of it. If you hear that sound, that's my 2-year-old behind me. I apologize for that. You have to name the connection. And so analog.in1 is the name of the connection. That's what that 1 means. And then 2BB5, again, the 5th breadboard port on the hub itself. And we'll show you a picture of that here in just a second. There are the 9 breadboard ports. The first 4 are digital, and then 5 through 9 have analog. So you have to make sure that you are using either a digital or an analog breadboard port for that.
So he pointed out that, Todd pointed out that there is no program in program, and there also is no for in for when you're setting loops. It's a coding language, and we don't have to define our variables on the 84Cs. We just run it as is. And so we're going to create a in for loop or a for loop, and so we want to connect to breadboard 5, that pin, and we want to do it, we called it in, and you could have named this whatever variable you want, and we're going to start with 1, and we're going to do it 50 times. So we're going to get 50 readings from this pin, from whatever we're going to set up. And so in this case, we're going to set up this temperature sensor, but that's what that means in, I guess, English, layman's terms.
And so with the CX, just like I showed you with the while loop on the brightness sensor, here you have a for loop. So you go to that control menu just like I showed you, but instead of the while and while, you pick the for and for. If then statements are in there, all of the different loops and statements are in that control module. And then same verbiage from there. You've got n as just the name of the loop that we're doing, and we're going to go through it 50 times. And so with the Nspire, it automatically builds that for and then the n4 in there for you. So all you have to do is then type in between them, and you don't have to remember later to put that line of code in.
And so in that loop, we're going to read the analog, and so we're going to read it. Just like we read the brightness earlier. And again, I kind of reminded everybody, don't forget to close quotes, close parentheses.
And the parentheses aren't needed on the Nspire CX, but the quotes are, because that's what is the device is learning what it's supposed to do. So here we connected the analog port to breadboard 5, so that was an important step to make sure that the hub knew what to do or where it was looking for the information. Now we're saying, now that you have that connection, let's read what's coming into that connection. And so that's the next part of our loop there.
And if we were paying attention when Todd talked earlier, so if I read it, I'm going to have to do something, right? And so I tell my students, you might have done your homework, but if you didn't turn it in, then I can't grade it. So read is the fact that the kids did the homework. The get is them turning it into me. And I say get because I'm from South Louisiana, and my students laugh at me as well. But I need to get that value for those 50 loops each time. We called it V for voltage.
And somebody asked before, is V a defined variable in the hub? It was over in the questions on this for brightness. It is. And then V, it knows that it's looking for a voltage, and so it's reading how much voltage is coming into that analog port. Stacy, I'm sorry. Did you mention at the beginning that what we're doing with this activity with the calibration of voltage to temperature?
No, I just said we were doing temperature, but
okay. So we're using a sensor that will read the voltage, and then from the voltage it will be able to convert that into temperature. So that's the actual program that we're doing here. It's a calibration activity where we can take the data that we get in voltage and convert that into temperature. And so that's what we're getting from the analog port.
So once I get it, I need to display it, and I'm also going to wait. And so just like we did with the brightness sensor, we will put a little note that says display, analog in is whatever V.
And you'll notice that the commands for the CX, again, are very, very similar. Very similar platforms. How you move around them are slightly different. There's little slight differences between them. But for the most part, once you learn how to do on one device, you can go back and forth really easy on the other devices. So same thing, we're going to display that, whatever it was that we got before. And then we're going to wait to go through to make sure that everything is going through the 50 loops, but it's going fast enough where if there's any changes, it can give us some good solid data there. And that ends the loop.
That ends the first program.
So now we're going to take you through what it actually looks like in the setup. So when you get the hub, there are accessories that come with it. And one of the accessories is the analog temperature sensor. And that's this picture here actually comes from the project and the activity itself. So you are going to connect the analog temperature sensor with some jumper wires. They're going to be female to male, so you put the analog temperature sensor into the female end of the jumper cable, and then you connect that to the breadboard. And if you notice in the diagram here, and again, I'll show you some pictures that I took of when I actually created this, but we've got going into BB5, because that was what the program said we were going to connect. So we need to connect to BB5, and then we have to send the voltage that is going through our system. And so and then it has to come back into the hub, so we have a complete circuit. So we have to connect to the 3.3 volt port on the breadboard, so that's the red one that Stacy is pointing to now, and then complete the circuit into a ground, which the first 7 going across the bottom, the first 7 ports are all ground ports. And so that's how we make our complete circuit. And then with this one, because we're sticking the sensor, we're going to be sticking it into a liquid, water in this case, we don't want water obviously getting into our setup. So you can use a drinking straw, a simple drinking straw that the wires go through. I took apart a stick pen and put the wires through the stick pen and put them in. However you want to do it, you want something where you can contain the wires and then seal the system off. I used a hot glue gun. You can actually use sealant caulk if you want, but you put that around just to make sure the water doesn't get into the wiring and into your hub, and obviously we don't want that. So there's what the setup looks like. And so the analog sensor, again, it comes with the accessories, so there it is plugged into the female end of the 3 wires. And then those 3 wires going through my straw setup. Again, very simple design that you can do. Actually, the hollowed out pen. One of the things that I discovered when I did this is that the hollowed out pen and the wires made a very, very tight fit, and so tight that when I realized I had skipped a step and tried to pull it apart, I actually ripped the jumper cables apart. So you may want to use something a little more flexible as you do this, like a drinking straw, that's going to be easier to manipulate with the wires. So live and learn, part of the engineering process, right? Make it better, make improvements. But again, across the top there is where you want to put some sealant where the sensor and the wires are connected. Put the wires inside of your tube, whatever it is, and seal that shut. Thank you. So here are picters of the Innovator itself. You can see that the red wire that was coming from the V out part of the sensor itself, that's going into BB5 because that's where we said that we were going to get our information from that we wanted to connect to. You could have written the program to say BB6, BB7, BB8, BB9. You just need to make sure that you connect everything into the right ports. And I can't tell you the number of times that when you are debugging a program and you're looking at the program, you're trying to think, where did I mess the program up? A lot of times it's just in the wiring. You just put it in the wrong port, and then you realize that, and you feel kind of silly about it, and you go back and you redo it. So then also in the bottom view there, that's of the sensor. You can see it's got the voltage and then the ground, and so you connect the VS into the voltage port of the breadboard. So that's the 3.3 volt port. That's the green wire. And then the ground wire gets connected into a ground. And so it's a little difficult to tell from that picture, but the brown wire is going into, and the green wire are going into the bottom row of the breadboard. That's where the ground and the voltage sources are. And then the red wire is going into the top row, and that's where the breadboard connections are. So that's the BB5 on top, the other two connections on the bottom. On the other side of the hub is the B data port, and so the B side of your mini cable goes in there, and the A side goes into the calculator. It's or whatever device you're using, the handheld for the Inspire, the CE, or if you're using, you can run this from a Windows-based device or a Mac-based device that has the student software, the teacher software on it. One of the things also that I've seen people learn the hard way is it is important that you put the B in the B and the A into your device. It does use digital electronics, which only has a flow of one direction. And so if you put the wire in backwards, then nothing will flow from your device into the hub and it won't work. So little things that people do that can cause the program not to work and cause some frustration along the way. You can either tell people up front or let them try it out and make that mistake and learn from the mistakes. Either way, again, it's based on time and goals of what your project is.
One of the things that I really like with the Innovator, Todd, is that if you're writing code and there's an error in the code and you don't catch it, and even though you did check syntax, the Innovator will actually beep. It's like it's mad at you. That's what I tell my students. And it's mad at you to say, hey, you didn't do something right. Unfortunately, if you mess up your wiring, you're just not going to get the data. So there are fail-safes with, in case you do have some errors in your coding. And then if the wiring, like he said, most of the time you just flip it and then it works.
And so then the program itself, again, it's designed to take the voltage, read the voltage like we said, and display that on the screen. But then we're going to convert that into a temperature. And so here's where we're starting to get to some of the content because we're actually going to look at the freezing and boiling points of water, and we're going to calibrate the voltage that we read to those temperatures. And so if you're in a science class and you're talking about phase changes and you want to get the temperature values, well, here's a way to do that. And then we're going to take this and we're going to make a linear equation. So as you're talking about best fit lines, you're talking about y equals mx plus b relationships. We're going to get two coordinate points. And so if you're talking, again, in a math class about point slope or taking 2 points and determining what the slope and the y-intercept are, now you can take this and really build in a lot of the math and science content behind the coding that we did that goes along with it. So you'll have an ice bath and you'll have some boiling water. You will run the program to get the analog voltage value at the freezing point of water. You'll do the same thing at the boiling point of water, and now you have your two coordinate points. You've got your temperature and voltage at 0, temperature and voltage at 100, and now based off those two coordinate points, you can now create your line of best fit, which we can use in order to now determine other temperatures. And so that's where we're getting to eventually in this is, okay, now that you've calibrated and you create your line of best fit, now let's see what room temperature is, get the voltage temperature, or get the voltage reading for room temperature, figure out what that should be, and determine your percent error. So that's now where we're going with the next part of the program.
So there is a program too, and this program too, you're using the data from before and your line. And this one we're going to connect to the analog in, and we're going to connect to breadboard 5 again, but it's a little different on the 84CE or the Nspire. We have to do what's called a prompt on the 84CE. We prompt meaning there's going to be some input by the user. And so we're asking the user what's the M from the information we just got, and what's the B, meaning the M being the slope and the B being the y-intercept.
And so you'll see on the Nspire program it's similar, except prompt in the 84C is called a request in the Nspire CX, so there's just a little terminology back and forth between those two. But again, we're going to request the slope that students got from the 2 coordinate points from before and the y-intercept they got from those 2 coordinates before, and those are going to be very important to the next part of the project here, where
so
we're going to use that information. So Stacy, go ahead.
Yeah, sorry. So we're going to do another for loop. We're going to read the analog coming in from our new temperature, our ambient temperature, or whatever you want. And then we're going to read it, we're going to get it, and we're going to display it. We actually defined that what the M was going to be times the X, which was our analog, and then add it to the B that the user inputted, and it's going to be C, which again, later will display that temperature to be in whatever C is. And so hopefully using the information from the first, the 2 data points, the boiling and freezing point, this new temperature should fall along that line, and using the mathematical equation and then also the user inputs.
And so, again, very similar. We called for the input request of M and B before, and then we put in the equation that we're going to use. The analog value that we get for the room temperature, that's the X value that's going to be in, and then that will determine what the temperature is from the formula that we had created before, and just using the linear equation formula. We're then going to display that in degrees Celsius, and that's going to come up on the screen. And it will go through this iteration, by the way, that we wrote the program here 200 times. You can modify that number as you seem fit. If 200 of those readings seems like maybe that's kind of overkill, change it and make it 50. And again, that's an important part of this process of talking with students of how many points do you need in order for it to be accurate. How many of these times do you want to go through this in order to know, yeah, this is good, or this is taking too long, I don't need all of these. So you'll learn how to modify the number of attempts that you need as you go through the programs more. So I actually ran this program here at school a few days ago. I went through and I did this setup with it, and once I got this information, I then went and created my graph and did the display on this, and I put all my information in, and when I did this, it came up and it told me that the temperature in my classroom based off the analog voltage that we was reading was 113 degrees Celsius. Something tells me that I had an error in there, and so then I had to try to debug and figure out what I did wrong, because the classroom was definitely not that hot. It's a great way to see if your kids actually understand temperature scales and hopefully have a clue that that is absolutely shouldn't happen. I realized that I had just set up my independent and dependent variables backwards, and I flipped those around, and everything worked out great. So again, a lot of learning in terms of content that's happening from the activity that you're doing, and being able to figure out where your mistakes are and persevere in problem solving like we saw in the mathematical practice standards before, and great questions to have the kids asking each other, or you working through with them as you're writing the program and now starting to get this data. And Attend to Precision was one of the math standards. In this case, maybe not precision, but accuracy, and making sure that the values that we're getting make sense. And then, of course, the next step is, okay, you have this temperature reading that the device is telling you. Is that accurate?
Yeah, so big in chemistry, big in physics is that whole percent error. And then being able to given whatever instrument you're using to measure versus what the students actually got, and so being able to calculate the percent error. Definite extension for this. I'm even seeing, Todd talked about heating and cooling curve data. In chemistry, we talk about colligative property, which is a big term for saying what happens if you put salt in water. Like, why do we add salt when we boil water to make pasta, but we also add salt on icy roads in the winter, right? So what are the effects of both? And so now, not only did you learn about temperature scales, You learned about collecting temperature data. You calibrated a temperature sensor or temperature reader in voltage, and then now you can add it to something real-world situation. In South Louisiana, we don't really use salt on icy roads, but we sure do make a lot of homemade ice cream and put rock salt on our ice when we're making it. So that kind of helps with that conversation. And so I did see that one person asked if I could show on the 84 CE the same button that Todd was doing. So I'll show you guys real quick. So this is the TI Smart View CE for the 84. And so it's very similar to what Todd was using a while ago. This was my program I was working a while ago. So I'm just going to quit and come up with a blank screen. So PRGM is the program button that we're going to use. Todd did a lot of everything in menu. We just going to use program. And so I can either execute programs that I have here, I can edit programs, or I can create a new. And so I'm just going to go ahead and create a new, and I'm going to call it today. I'm actually not going to type it all out because you have to type it on 84. And then so I want to edit that one. So I'm going to go back and edit. It didn't save today. What did I do? Okay. Let me come back. Create new. TY. Hit enter. All right, so there's my program. If I wanted to do exactly what Todd did a while ago, or myself, let's say if we're going to go and turn the red light on, everything is still in program. Hopefully this looks very similar to what Todd had a while ago. And so I have some of the same similar commands that Todd had. Mine are just kind of in the different places, and I can still send set what I did a while ago, and I set the color red, so I'm going to come and do color red, and then I'm going to send set color red. I'm going to come back to program, and then go to hub, and under settings is where I'm going to find on. And so like I said, I'm going to make sure I close quotes. Oh. I'm going to close quotes and close parentheses. So very similar to what Todd was doing, just a few different buttons, I guess. I really hate to do like button pushing, but sometimes with these WebExes, it's kind of hard to do anything else. So I did see that somebody had asked that. Is that good? Is that what you were looking for? Whoever that was. At some point, there you go. So Deborah, hopefully that was helpful for you, Deborah.
While we're actually answering questions, yes. Fred had another question. He was wondering what level would you expect these courses to be set up for?
So there's the different programs in there. The Path to STEM and the Science and Engineering Design are really designed to be anywhere from middle school on up. The main course that I'm teaching right now is a physical science course. It's mainly for sophomores who have struggled with the reading and the writing, and I have done this, not this particular project, but one similar to it with that level of student, and they've been awesome with going through and setting things up and going through and doing different experiments. So it really is designed anywhere from middle school up through college and can be incorporated in. And one of the beautiful things about all of these is they're adaptable. And once you start playing around with it, the ideas that you come up with are amazing. We've got a user group for this, and the things that people come up with where they're syncing innovators together to make different music, and they're creating just, it's amazing what you can do with them really from any level. So middle school all the way through college really is what they're designed for.
So Fred, I had a STEM club at my previous school that was 6th through 12th grade. I had 6th graders and I had 12th graders. I had all grade levels, and they all were learning. I had some kids who were on the robotics team who understood the programming language that they use for their robots, but they had never used this before. So I actually started them with the 10 minutes of code for the TI Innovator. We are an Inspire district, so I only use Inspires with them. But I promise, as soon as I started showing them just some of the basic getting started in Unit 1, they were already asking about loops. Can we do this? And I tried to apply it to real-world situations. For example, in my classroom, I have a fancy lights when you walk in, the lights come on. When they come on, when you leave out of the room for 15 minutes, they go off. And I said, well, how does the light switch know that? So we actually wrote a program to simulate what happened in my classroom. So any grade level, I did STEM camp this summer. That was 9th and 10th grade. We actually took some of the modifications or modified what Todd was talking about thinking innovators, and we played the Star Spangled Banner and had red, white, and blue LED lights on with the music. The kids will do it. It doesn't have to be teacher-led, and I think that some of the concerns for teachers is that I don't know everything and my students have to know, but feel free just to play with them. I think that's kind of part of it, is just having that play time.
And there is for sure some vulnerability here. I will say for myself, there's vulnerability in me doing this presentation, because I know from working with people that there are people who are so much better than me at doing this, but you learn the little at the beginning with those 10 minutes, and then you just get better and better and better and better at it, and the kids will ask you for more the more you use it in the classroom. There was another question that I wanted to get to if we have time for that. The question was, where is the analog temperature sensor? Stacy, could you throw this over to me?
Yeah, sure.
All right, share. So in the presentation, there were some links in there for you to take you to all of this information, so you can follow the links that are on the last slide of the presentation. But on the Innovator itself site, which would be under Products and TI-Innovator Hub, there's overview, specs, and accessories. So in the accessories are where all the different packs are and then what come with them. So the specific question is, where do you get the analog temperature sensor? That's in the breadboard pack. Here's a nice fancy diagram of everything that's in it, but it's all spelled out over here for you of exactly what comes with everything in the breadboard pack. And then there's some other external devices that you can use and purchase also. The packs are, I don't know the exact cost, it depends on the distributor, but all of them are relatively cheap and inexpensive to get. And like the jumper cables and those kind of things, they're available all over the place. So, but specifically the temperature sensor that we used was this little guy right down here that comes in the TI-Innovator breadboard pack. All right, Stacy, back to you if you want to show that slide.
So the materials that come in the breadboard packs were designed to be considered to be consumables. That it's okay if you apply them or use them in projects and they hot glue them or strip them or use them for things. That it's not like you're messing up the innovator and you didn't have to solder things together. That's why how the breadboard is made. So like Todd was mentioning, they are inexpensive. There are other sensors out there. There's other pieces. Like there's an ultrasonic, there's a range finder that you can add to this. There's a humidity sensor. So there's other sensors out there that it's really limitless. It's you and your students can design more projects. TI just kind of said, hey, here's some basics of where to go, and then therefore you can add on to it. So Mike, you ready?
I'm ready.
All right.
So earlier, Stacy mentioned that we're excited to have the T-Cubed International Conference coming to San Antonio this year. It's really a great place to get your hands on a TI Innovator, for example, if you haven't seen one or played with one, as well as meet Stacy and Todd and connect with them and learn from them. So we really hope that you will be joining us at the T-Cubed International Conference. Also, Stacy mentioned that we're giving away to one lucky winner conference registration for the T-Cubed International Conference, and tonight's lucky winner is Phyllis Clark. So Phyllis, congratulations. We'll be in touch over email in the next few days to give you more information. To receive a certificate of attendance, go ahead and click the link in the chat window. Also listed is a link for the documents tonight. Just be aware that we did notice there was a small error in the documents folder, That error will be corrected in a follow-up email that you're automatically going to get within a few days. So if you're really chomping at the bit to start looking through some of the material, feel free to use that documents link to get all the documents that were used tonight. But if you can hold on for a couple of days, you'll automatically get the corrected documents in a follow-up email. That follow-up email will have a link to the recording, a link to the documents, and a link to the certificate as well. Thanks so much, Todd and Stacy, for everything that you shared tonight. I know, Stacy, you're going back to school tomorrow, so have a great first day back, and the same goes to everyone else out there that joined us tonight. So, again, thanks so much, Stacy and Todd, for everything you shared.
Sure. Can't wait to see everybody in San Antonio.
Yeah, and I was just looking at where everybody was from. It's just great to connect with everybody from literally across the world, and hopefully everybody got at least one thing out of here. To me, that makes a successful conference. You have our contact information on the slides you'll be getting, so feel free to ask us any questions that come up along the way. Our job is to help you guys out and help kids learn across the globe, so let us help you do that if you have any questions.
Thanks again, everyone. We hope to see you back online next week. Have a great night.